Where's that cool little full screen button? Boom. All right. So as Nick O'Brien mentioned previously, this is on a paper written by researchers from the College of William and Mary. And it's called Whispers in Hyperspace, High-Speed Covert Channel Attacks in the Cloud. And it basically covers the method of a covert cache, or a covert channel between CPU cache in a cloud infrastructure. So just a little background on this paper. It was presented at Usenix 2012, and it was published in the IEEE Journal with Transactions on Networking in December 2013. And just a quick overview. So as a CPU cache-based covert channel, obviously the CPU cache that exists on almost every modern CPU you can think of in existence. So it's a pretty versatile technique, even though some of the components after that are slightly different based on the architecture. So I feel like this paper is important because covert channel attacks between virtualized instances in a cloud environment, like that could happen today. There's nothing to really prevent that, and it's versatile. Most clouds nowadays run on the x86 platform under a known hypervisor. And it proves a reliable method of communicating between two VMs, even if they can't connect over the network or really any other way. And it just utilizes the hypervisor's physical hardware. So cloud hosters like AWS, DigitalOcean, Google Cloud are the main platforms that are being targeted by this, because who knows who you could be next to on the same physical server. Really anybody else, any company, individual could have a virtual EC2 box on the same physical server as the one you're running on. So a couple related works. The Orange Book was mentioned in this to say that basically just as a baseline for a covert channel technique. And they mentioned that 1 bit per second is really an acceptable covert channel. Some people would say that's not really an acceptable bandwidth for a covert channel, just because it's not fast at all. It'll take a very long time to transfer any information. But that's kind of like what the standard was going into this research field, because nobody's really done it before. The first paper mentioned here. So hey, you get off my cloud is they were one of the first people. Yeah, Nick?
Do you offhand know when the Orange Book was published?
No, I do not. No, I do not. That's a good question. Yeah, it was quite a long time ago. This first paper was actually published in 2002. It was one of the first papers to cover this covert channel technique. And they achieved a throughput of like 0.2 bits per second, which, according to the Orange Book, isn't really an effective covert channel technique. So up until then, it was kind of seen as potentially viable or even not viable, even though the channel existed physically. The second paper mentioned here, an exploration of L2 cache covert channels in virtualized environments. So they further discuss this research implementation of a cache-based covert channel. And they actually achieve a theoretical 1.77 bits per second of throughput, which is an acceptable means. And this was published, I believe, several years after that. And I have links to both the presentations down in the note to this. So the second paper was actually published in 2011, and the first one was published in 2009. So the preliminary research that the authors did on this I would say group of techniques was that there were significant limitations in how you could utilize this cache-based covert channel in virtualized environments. So the old way worked mostly on physical hardware. So you say you install an operating system directly on the physical hardware and do it within the operating system as processes. So that's what really worked pre-virtualization, excuse me. And the three main issues that they address are, or they figure out that they have to address are addressing uncertainty, scheduling uncertainty, and cache physical limitations, which we'll get into. So, by the way, if anybody has any questions or comments while I'm going along the presentation, feel free to just raise your hand, yell it out, so we can just like keep it flowing. But also, you know, there might be some topics that you might be interested in but don't quite know, and I might be able to provide some insight, but just letting you know. So the addressing uncertainty is a kind of an interesting problem. With the classic covert channels, you really, the process needs to have knowledge of the mapping between the virtual memory and the physical memory. So as a userland process in any modern operating system, you won't actually get the physical address to the system memory, right? You'll get a virtual address provided by the operating system to like section away, to abstract that information. But since in a virtualized environment, there's two layers of virtualized mapping, address mapping. One that happens at the operating system level, as you can see here. So this basically just represents two VMs connected to the hypervisor with the CPU cache in the middle that would be used as a covert channel. And so the process, right, is mapped with a virtual address to the guest physical address. And in this case, the guest physical address is actually the hypervisor's virtual address that it's giving to the VM. And then the host accesses its memory with the physical address. So from the process level, it has to go through the OS virtual mapping and then the hypervisor virtual mapping in order to get that information of how does the virtual address, right, that I have map to the physical address on the physical system memory. And that's super important because cache nowadays, which I'll get into in a couple slides, but I'll give it a little TLDR, is physical memory is mapped to certain placements in cache. So if you don't know where these placements are, it's very difficult to determine the specific memory that you're trying to access or that your receiver or sender might be accessing for the covert channel. So scheduling uncertainty. In the past, with the classic covert channels, the receiver has to plant some information in the cache, the sender has to modify it, and then the receiver detects the changes that occur between the iterations. So this means they can't be operating in the same in parallel, right? One has to go, then wait for the other, then the other has to go again, and that introduces kind of like a timing challenge, especially since in the new way you don't actually have knowledge if you're accessing the same memory, like cache section, or cache line rather. So that's definitely a problem that they come up with. And it can't be done since the cache can be modified at any time. So the VM might be descheduled on the hypervisor itself, and then other VMs are running at that time. So that'll kind of dirty the cache. The cache could change randomly based on however many number of VMs are running on the hypervisor at that time. And that means that if the sender and the receiver are operating at the same time, in any case, then it's very difficult to provide, to access the same memory that would lead to this cache being changed. So the third one is physical cache limitations. In previous covert channels, in no way could you operate a covert channel between physical processor sockets on the server motherboard. They've had to be running on the same physical processor, maybe on different cores, but the same physical processor. And that's because of this L2 cache that each processor has, because that was used as the method for the covert channel. So nowadays, there exists an L3 cache in place of this L2 cache, and each core actually has the L1 and L2 cache as kind of like its own resources. So just to reiterate, classic cache channels can usually achieve transmission rates up to like 400 kilobytes per second, which is pretty fast for a covert channel. You usually see bytes per second, like maybe less than 1,000 bits per second in covert channels, maybe not even a byte, which is it's pretty good. But under virtualized workloads, this same covert channel, the same algorithm, only achieves around 1 bit per second. And that's a drop of several orders of magnitude, over 3 million bits per second reduction in bandwidth for this covert channel, just moving to a virtualized workload. So that showed the authors that they really had to redo this whole scheme for the covert channel. So I'm just going to give a quick how does cache work, so we can understand a couple of the next things for how the authors actually designed the data transfers for the covert channel. Excuse me. So the main thing I want to cover is how cache actually caches memory, right? So there's things called cache placement policies, and the most general one that's used nowadays is actually a mixture of two. It's a mixture of direct memory mapping, which means that a physical address is mapped directly to one of these lines. So let's say block 0 is mapped directly to line 0. And also associative mapping, which is when any block of memory can be placed in any cache line. The problem with that is if you have to search through the cache because you're not sure where the memory is being placed, that's a very taxing operation that they kind of don't want to do. So what they came up with was a mixture between the two, which is called set associative mapping, which basically says, say you have a bookshelf and you have 4 books, right? The first shelf can have these 4 books, and the next shelf can have these 4 books in any order. So that really allows you to search through 4 placement spots instead of the entire cache. So the new approach that they go on to is now transferred based on the latency of the memory operation itself. So if the data resides in the cache, it's a very fast memory operation. That's called a cache hit. And if it's a very slow operation for the memory retrieval, that's called a cache miss. So basically, instead of using the method where the receiver has to set data in the cache and then remember that, the sender has to modify it, and the receiver reads it again and detects that change. We basically go on to more of a clock cycle based channel. So if it's a 1, it's a 1, and if it's 0, if it's a 1 or a miss, a cache miss, so the data they were trying to receive is not in the cache, that's a miss. And then a cache hit is a very quick operation, so it was in the cache. That's a 0. So this means that data can actually be transferred in parallel, which is super important because as servers nowadays, and even processors in general, now are being made with a higher core count, there's a higher chance that both your VM and somebody else's VM are going to be running at the same time, in the same real time as each other, because there's just more cores to provide computational resources to VMs as a whole. So they did have issues with this timing channel based on cache alone. It is high bandwidth, but when no other workloads are happening on the same server, so when just 2 VMs are running, it's not too bad. But as soon as external workloads, other VMs, start running on the same machine at the same time, that creates a lot of noise that they kind of didn't account for in one of their models. So it was pretty difficult to establish the stable channel between the two, the sender and receiver. So they decide on looking at the memory bus, because the memory bus is actually being used to interconnect everything within the multiple CPUs and the system memory. And it delivers data between components. And they name this the bus contention channel. And we'll get into why. So at this point, this is very x86 specific. So this won't necessarily work on ARM processors, MIP processors, VAX architecture, or anything like that. They do mention the VAX architecture, if anybody knows what that is, due to specifically providing an implementation to mitigate this covert channel. So the VAX does not allow contention to occur, or basically contention to occur on the memory bus, because that slows down the entire system. So the most interesting part that was kind of hard to wrap my head around was these atomic instructions and how they provide to the contention of the memory bus. So the atomic instructions, are basically just instructions designed to facilitate multiprocessor synchronization. So just think mutexes and semaphores in threading, right? If you need one thread to access this resource at this time and nothing else can access it, that's why you use a mutex. And that's kind of like a hardware lock on this block of data in memory. So that means no other cores can access that data while the one core has this atomic action on it, or releases the atomic instruction. And they also mention exotic parameters, providing exotic parameters to this atomic instruction, which we'll get into exactly what that means later. But just think very rare to encounter. And an example they use is memory being misaligned in memory, or memory being misaligned. So think in C, where you have strict placement of how structs can be created. So if the memory is misaligned at that point, most times the compiler fixes that for you without you knowing, which is why it isn't too rare nowadays. But just think that for exotic. So the thing they get to with newer processors, or newer architectures, they don't necessarily have a shared memory bus anymore, like the previous architectures did. So they have to develop kind of a new way around this for some aspects. So basically, each processor, if you have a multiprocessor system, has its own bank of memory. And if you physically look at a server nowadays, you can see that the memory is physically aligned around the CPUs and not just in one bank itself. And that's because that's the main memory for those CPUs. And Intel and AMD actually divides the technology so that the CPUs aren't just limited by their own memory. They can access memory for other CPUs as well, which is slightly more costly, but it can be done. And that's called the memory interconnect. Quick path interconnect is basically the technology in place. So for this example, let's say a cache line is 64 bytes, right? So if we go back to how that cache works slide, one of those lines that maps to memory is 64 bytes. So with these atomic instructions, basically what happens is if you can execute an atomic instruction that says, I want this memory to be locked just for me, and the memory goes 2 cache lines, is on the border of 2 cache lines. So let's say you use the middle 64 bytes in the 128 byte block. So that actually provides an exotic, I guess, function in nature that the manufacturers didn't really account for, but they kind of accounted for. It's more of an EE problem than it is like a computational problem. But basically what happens is that a lot of traffic gets generated on the memory bus, or in this case, the interconnect, because all the CPUs, to ensure that no other core or even physical socket has access to that memory, is that cache is flushed, right, out of these other processors. And that's what creates a lot of traffic on this memory bus. And another important thing, all in-flight memory operations are terminated. So if one processor is requesting to access memory while this atomic instruction is executed, it's totally canceled. So that's one of the other things that provides to this, this contention on the memory bus, which creates the latency we're going to see. So these are some of the initial tests that they completed. And something that I found was kind of cool is that they actually did this on totally different platforms. So the graph on the left is with an Intel Core 2 under Hyper-V between Windows guests, and the second one is the newer architecture, totally newer architecture on the Zen hypervisor, which is Linux in nature, and running Linux guest VMs. And the initial bandwidth that they get is around 38 kilobits per second, which is pretty good for this covert channel, considering the previous implementation in 2011 was around 2 bits per second theoretically, and they actually achieved this in practice on their own environment. So it's definitely slower than normal cache-based implementations, but again, this is under a virtualized workflow, so it's a much different environment. And another interesting thing to note is that this works between physical processors. It's not just limited to cores on one processor. So if we go back to that diagram, right? The old covert channel method, it only worked if the VM was also running on CPU 1. But now the channel they develop actually works between all of the cores on all the CPUs. And that's just due to the interconnect and how the latency affects that. So a couple of problems they ran into is the algorithm they're using is prone to errors since it doesn't account for noise from other workflows. So say if 4 VMs were running and only 2 of them were the sender and receiver, so the other 2 were doing like legitimate operations, it creates a lot of noise on the memory bus that they didn't essentially account for in their algorithm. And this graph, the red is basically other workflow that's going on at the same time their covert channel is trying to send data to each other. And you can see how it's kind of hard to tell anything was going on based on this last diagram we have here. So obviously the high peak is a 1 and the lull is a 0. And with this graph, you cannot tell that they're trying to do anything at all. So that actually affected their algorithm. And the descheduling of VMs, they also didn't account for. So when their VM is actually stopped at the hypervisor level, and then another VM is now running, it's kind of like paused. So their new communication protocol, it involves basically a confirmation that the receiver actually received the data. And they use the bus contention method as a way to do that as well, which is a signaling method for the sender. Clock synchronization, they used an algorithm that was already created called the differential Manchester encoding algorithm to make a self-clocking mechanism. And this was actually used in token ring networks back in the day. For error correction, they used the Reed-Solomon coding, which is basically just a parity-based encoding, which is used in satellite communications and also RAID 6, if you're familiar with how RAID works, RAID 5 mostly. And they implemented also data frames, so they could chunk up the data so they didn't have to send it all at the same time, which was pretty useful. So they have like 2 sets of final results, one on their self-hosted infrastructure and the second one on Amazon EC2 between 2 instances. And basically, they profiled the machine to determine the optimal data frame size, so how much data they would send at once, and the error correction strength, so how many parity bits they would use for each bits of data for each bits of data they were sending. So this architecture had no shared memory bus, so it was on the processor interconnects. They sent 1 kilobyte block of data per transmission, and over 50 transmissions, they got a bandwidth of about 746 bits per second, which was pretty good, and the error rate was very low, under 0.1%, which means that this is a very good covert channel, because if the error rate was high, then it's very unreliable to transfer data between the sender and receiver. So on EC2, this had a shared memory bus, and when they profiled it, they got a bit different data frame size, and they accounted for that with the parity for other workflows, which wasn't too bad. Between the first 12 to 15 transmissions, the 1 kilobyte block they were sending, they got a bandwidth of about 343 bits per second, which is actually pretty good, with a decently low error rate, 0.4, which it doesn't really affect because they have an error correction in place anyways. And they did run into some problems when the performance started to degrade, and they didn't know why at first, but they basically figured out it was the way Zen schedules VMs on the hypervisor itself. So Zen works on a credit-based system. So let's say your VM gets 100 credits, and it can use them throughout a second, right? If the VM has already used its 100 credits in half a second, then Zen is like, OK, get out of here. We're putting another VM to run on right now. And VMware has the same type of implementation. They're just called shares. So that totally threw them off, because their performance degraded way below what they thought it would be. So kind of how they dealt with that is they adjusted their algorithm to adaptively change their bandwidth between the sender and receiver, so how many bits they sent at once. And so what they did is they just dropped, when they were at a high credit count or low credit count, they dropped it to about 50 bits per second, and then raised it back to around 200, 300 bits per second for much faster transmissions. So they also go over some of the mitigations that can be provided against these covert channels. And for most of them are for cloud providers and hardware manufacturers. They cover what a tenant could do to kind of see that this was occurring, but there's nothing you really can do as a tenant on these types of environments. So probably the best thing you can do is use a dedicated host in EC2, but those are 6 times more expensive than traditional EC2 instances, because you get a whole hypervisor just to yourself, basically. So, I mean, if you're super paranoid, that's the way to go. Or cloud providers could use hardware counters. So there's actually counters in the CPU itself that can be queried that basically say how many times was this CPU instruction used, and then you can trace that back to see if anybody's using that for malicious intent, potentially. Hardware manufacturers could trigger a trap instead of performing the exotic action that created the contention on the interconnects or the shared memory bus. And a trap is basically just an exception or fault that happens at the hardware level that signals to the operating system that they're going to have to handle it, or that it doesn't even complete the operation. So basically, covert channels in cloud environments are totally practical, and they can 100% be done right now on EC2. So with over 100 bits per second in bandwidth, it's a totally viable option to use this as a covert channel. And it's also very cross-platform. They use different architectures, different operating systems, and different hypervisors. Just you need to stay on the x86 architecture because it's very specific how that operates based on how instructions affect the memory, basically. And a couple things that they mentioned for future research. Since a cloud provider has so many more resources than the tenant or hardware manufacturer sometimes, so providing covert security to them in order for tenants to utilize that is like a huge business thing as well as a security thing. It could give AWS potentially an edge, a huge edge over competitors such as Google Cloud who don't have the security feature implemented. They also mentioned a couple questions from the Q&A, which I actually watched. They streamed this or they recorded it online and posted it up later. So they basically, a dude from Qualcomm basically asked if it was possible to have multiple receivers to get a higher chance of landing 2 VMs on the same physical server. And they basically said, yeah, it's possible, but they already spent 2 days and over a few hundred EC2 instances in order to get 2 VMs on the same infrastructure to test with. So it's kind of like a toss-up. It's definitely going to be some brute forcing. And he also asked about the instruction cache. So this presentation in nature goes over the data cache specifically that accesses the data in memory. There's also a separate cache that is used to cache instructions, which I thought was super interesting because I didn't think of that while reading through the paper at all. And they said they didn't consider it, but it would definitely be worth pursuing. And these are just a couple of the sources I used, the source from the paper, and then the actual link to the Usenix website. And that's all I got. Any questions? Didn't think so. Yeah. Yeah.
Do you think that there's any possibility, like with respect to the article that was talked about, somehow use some type of covert channel similar to this?
For sure. If the chip was like placed correctly on the motherboard, you could definitely use that to communicate data. I would say for sure.
Okay.
Did that answer your question?
Yeah.
Okay. Yeah. All right, cool.